Welcome back for another deep dive. Looks like we're taking a close look at the IE 754 2019 standard for floating point arithmetic today.
That's right.
And more specifically, you're interested in learning about these new augmented operations with a special rounding mode.
Yes, particularly how to emulate these operations using existing hardware.
Okay.
So to start off, the IE 754 2019 standard actually updates the 2008 version.
Okay.
And it introduces 3 new operations: augmented addition, augmented subtraction, and augmented multiplication.
So 3 new operations.
3 new operations, and they're all designed to help make numerical calculations more reproducible.
Reproducible, so like getting the same result every time you run the same calculation.
Exactly.
Why is that a problem with computers? I mean, aren't they supposed to be good at being consistent?
You would think so.
Yeah.
But the thing is that floating point arithmetic is a little quirky.
Floating point arithmetic.
Yeah, it's the way computers represent real numbers.
Yeah.
And because they can only store a limited number of digits, there are inherent limitations. It's kind of like trying to squeeze the entire script of a movie into a single tweet.
Huh.
You would have to cut out a lot of detail, right?
You'd have to, yeah.
It's kind of like that.
So some details get lost.
Exactly.
And that's where rounding comes in, right?
Uh-huh.
It's like smoothing out the rough edges.
Exactly.
Okay.
So the standard way that computers round numbers is called round to nearest ties to even, or RN0 for short.
RN0.
It's like trying to find the closest parking spot to the store entrance.
Right.
If you're exactly in the middle of 2 spots, you pick the one on the even side.
Okay.
But these augmented operations use a different rounding direction called round to nearest ties to 0, or RN0.
Okay, so a new rounding direction.
Yeah.
Why do we even need this new rounding mode? What's wrong with this standard one?
Well, RN0 can significantly improve the reproducibility of certain numerical computations.
Okay.
You see, when you perform multiple calculations in a row,
Uh-huh.
those tiny rounding differences from RN0 can accumulate and sometimes lead to slightly different results depending on the order of operations.
Interesting.
With RN0, which always rounds to the number closest to 0 in those halfway cases,
Yeah.
we can minimize those discrepancies and make the calculations more consistent.
So it's all about consistency.
It is.
But how do we actually get computers to use this new rounding mode?
Though ideally, these operations would be built directly into the computer's hardware.
Okay.
But that's not always feasible.
Right.
That's where emulation comes in.
Emulation.
We can use existing hardware and algorithms
Right.
to mimic the behavior of RN0 rounded.
Okay, cool. So we're going to be talking about emulating augmented addition and augmented multiplication.
Yes, that's what we're going to focus on.
Okay.
And the key here is to emulate these operations using the conventional floating point operations with RN0 rounding that's already available in hardware.
Okay.
And to do that, we need to start by understanding radix 2 precision 4 floating point arithmetic.
Radix 2 precision 4.
Yes.
Could we break that down a little bit?
Of course. So radix 2 simply means we're working with a binary system.
Okay, the language of computers.
Exactly.
Zeros and ones.
All those zeros and ones. And then precision point refers to the number of bits used to represent a number.
Okay.
It's like the number of digits we're allowed to use.
More bits, more detail.
Precisely.
Okay. And how is a floating point number structured?
So think of it like scientific notation, but for computers.
Okay.
It's expressed as mp2x plus 1, where m is what we call the significant.
The significant.
That's the significant digits of the number.
Okay.
And x is the exponent, which tells you how big or small the number is.
So the significance, like the main part of the number, and the exponent tells you where to put the decimal point.
Exactly. Now, within floating point numbers, you also have what are called normal and subnormal numbers.
Normal and subnormal.
Yeah, normal numbers are like the standard way of representing numbers,
Okay.
while subnormal numbers allow us to represent values very close to 0.
So like a zoom function to look at the tiny numbers.
Yes, exactly.
What are the smallest and largest numbers we can represent?
So the smallest positive normal number is 2mn,
Okay.
where mn represents the minimum exponent value.
Right.
If we include subnormal numbers, the absolute smallest positive number is 2mn plus 1.
Okay.
And the biggest number we can represent is 2 plus 1x, 2 Emax, where Emax is the maximum exponent.
Okay, so we've got boundaries
We do.
on the numbers we can handle.
Right.
And what about those rounding functions?
So RN0 and RN0,
Yeah.
we can visualize them. Figure 1 in the source material provides a great visual representation of both rounding functions.
Okay.
And it highlights those halfway cases where RN0 and RN0 differ.
Okay, so the real magic happens in those halfway cases.
You got it.
All right, now that we've set the stage, I'm ready to dive into those algorithms that make this emulation possible.
Let's do it. So to emulate these augmented operations, we first need a way to express the exact sum or product as the sum of a rounded value and an error term. And that's where these algorithms come in. Fast2sum, 2sum, and Fast2mult.
So Fast2sum and 2sum sound like they're for addition.
Yeah.
And Fast2mult is for multiplication.
You got it.
Okay.
They each serve a slightly different purpose,
Right.
but share a common goal.
That's that.
Breaking down an exact result
Uh-huh.
into a rounded part and its error term.
So essentially, these algorithms help us figure out how much rounding dust is created
Yeah,
when we do these operations.
precisely.
Cool. Let's start with Fast2sum.
Okay.
I'm all for simple and efficient.
Well, it is surprisingly simple and efficient,
Okay.
but it only works under certain conditions.
Like what?
So it works best when one of the numbers is 0,
Okay.
or when the exponent of one number is greater than or equal to the other.
So basically, it calculates the rounded sum of two numbers.
Right. Yeah.
And then uses a clever trick to extract the error term.
Exactly. And in these cases, the calculations are exact.
No additional rounding.
No additional rounding needed.
That's pretty neat, like finding a shortcut. Through a complicated maze.
Exactly.
What happens when those conditions aren't met?
That's where 2sum comes in.
2sum.
It's like the reliable workhorse
Okay.
that can handle any pair of floating point numbers,
Regardless of their exponent.
regardless of their exponents.
So it's like our trusty backup.
Yes. It involves a few more operations than Fast2sum,
Okay.
but it always gets the job done.
Okay, and Fast2mult, you mentioned it uses FMA.
Yes.
What is FMA?
So FMA stands for Fused Multipliad,
Okay.
and it's a powerful instruction that combines multiplication and addition into one step. The advantage is that it minimizes rounding errors
Okay.
that might occur if we perform those operations separately.
So it's like a streamlined assembly line.
Yes.
Less chance of errors.
Exactly.
Okay, so Fast2mult uses that to efficiently decompose the product
Yes.
of two numbers
Yes.
into its rounded value and error term.
That's right.
Okay, you mentioned limitations earlier.
Yes.
What are some of those situations where they might not work perfectly?
So Fast2mult, for example, only works when the exact product falls within a specific range.
Right.
If the product is too small, it can't be accurately represented as the sum of two floating point numbers.
It's like trying to measure the width of a human hair using a yardstick.
Exactly.
Right tool for the right job.
Precisely.
Okay. What about Hauser and Sturbin's lemmas? What role do they play in this?
Those are like helpful guides,
Okay.
providing shortcuts in specific scenarios.
Okay.
So Hauser's lemma tells us that if the rounded sum of two numbers is subnormal,
Subnormal, those tiny numbers.
yes, those tiny numbers close to 0,
Yeah.
then the exact sum is also a floating point number,
Yeah.
meaning we don't need any fancy calculations to get the exact result.
So we can skip some steps.
Exactly. And then Sturbin's lemma deals with subtraction.
Okay.
It states that if one number is between half and double the value of the other, their difference can be calculated exactly.
So these lemmas are like cheat codes
They are.
for certain calculations.
Exact-
Now, what about this Harrison's ALP?
All pH.
Yeah.
Okay, so all pH or Harrison's ALP is a slightly modified version of the unit in the last place function.
Unit in the last place.
Yes.
Okay. And why use ALP-PH instead of the standard ALP?
So the standard ALP function has a little quirk.
Okay.
It behaves inconsistently at powers of 2.
Okay.
All pH smooths out that inconsistency, making it more reliable for our purposes.
So consistency is key.
It is very important
Why is ALP-PH so important for this emulation process?
because it helps us bridge the gap between the standard RN arrow rounding and the RN zero rounding.
Okay.
RN zero chooses the number closest to 0 in those halfway cases, and all pH helps us detect those cases and make the necessary adjustments.
Gotcha. So it's like a special decoder ring.
Yes, exactly.
Okay. And what does the MILE-PH algorithm do?
So that's algorithm 4 in the source material,
Okay.
and it calculates LPH for a given number A.
Okay.
It's a fundamental building block
For the whole process.
to the whole emulation process.
You mentioned that radix 2 is important for this to work.
Yeah. Yes.
Why is that?
The logic behind my LPH relies on the fact that we're working with a binary system.
Okay, that radix 2.
That radix 2 we discussed earlier.
Yeah.
It wouldn't work directly for a decimal system.
Like the one we use every day.
Exactly.
So it's like a recipe that only works with specific ingredients.
Yes, a very specific recipe.
We've covered a lot. Algorithms for sums and products, cheat codes, and even a special OLPH calculator.
We have all the pieces in place now.
So we're getting close to understanding that emulation magic.
We are getting very close.
All right, we're back and ready to tackle this recomposition algorithm.
Sounds a bit intimidating, doesn't it?
It does a little bit, like we're going to be piecing together some numerical puzzle.
That's a great way to think about it.
Using all the tools we've discussed.
Exactly. So algorithm 5,
Okay.
called recomp in the source material.
Recomp. Okay.
That's the key to it all.
All right.
Remember those outputs? Pia and...
Yeah, from our fast to sum and all that.
From fast to sum, or fast to mult. Recomp takes those values and transforms them into yi and nan,
Which represent.
the rounded value using r and 0 and the adjusted error term.
Okay, so it's like we're taking those raw ingredients
Uh-huh.
and refining them to match our desired R and 0 rounding.
Precisely.
But how does recomp actually work?
It all comes down to those halfway cases.
Those tricky halfway cases.
Exactly where r and 0 and r and 0 differ. So recomp uses mile pH.
Our old pH calculator.
Yes, to determine if the initial rounded value, Heldrum, needs adjustment.
Okay.
And if it's a halfway case, recomp uses that calculated pH value to make the necessary tweaks resulting in Heldrum.
Okay.
But of course, it also updates accordingly.
To make sure everything stays balanced.
To ensure that Na plus Loro remains equal to the original exact sum or product.
Gotcha. So mile pH is like the detective and recomp is the artist
I like that analogy.
making those final adjustments.
Yeah.
But you mentioned a constraint on yours.
Yes.
For recomp to work.
Right.
Something about needing to be larger than 2 Amen.
You're exactly right.
Okay.
That constraint is crucial.
Why is that?
If the absolute value of 8 is too small, mil pH won't give us reliable results. And the whole process can fall apart.
Okay, like using a telescope to see something right in front of you.
Exactly.
Okay, so recomp is our magic ingredient.
It is.
But it relies on those earlier algorithms.
Right.
And it has that constraint on no.
Yes.
Now, how do we use it for emulating augmented addition and augmented multiplication?
Excellent question. Let's start with augmented addition.
Okay.
Algorithm 6 is called AA simple.
AA simple.
Provides a straightforward approach, assuming our results are finite numbers.
Simple sounds good to me.
It is quite simple.
What's the basic idea?
So first, it ensures that the larger of the two input numbers, x and y,
Okay.
is used as the first input to fast to sum.
Okay, to satisfy that condition.
Exactly. Then it calls fast to sum to get no and no, and feeds those into recomp to get our final no and nux.
So the numbers run fast to sum refine with recomp,
You got it.
but I'm guessing there are some catches.
There are a few.
Like what?
So, for example, if the absolute value of the sum equals a plus 2 massacet,
Okay.
A simple produces positive or negative infinity for both nats or not and not,
Right.
but with opposite signs.
Okay.
However, according to the standard, the correct result should be not equal to positive or negative A and not equal to positive or negative 2 not max, both with the same sign.
So it gets the magnitude right, but messes up the sign.
Exactly.
Yeah, that's not great.
And there are other tricky situations, too.
Oh, no.
If the sum is actually larger than A plus 2,
Yeah.
A and simple can even return a nan,
A NAND.
which means the computer doesn't know what to do.
Not good.
No, not good.
So AA simple is efficient,
It is.
but it has its limitations.
It does.
Is there a more robust solution?
There is algorithm 7, or A-full, is designed to handle those overflows and edge cases.
Okay.
It builds upon AA simple, but incorporates additional steps
To be more robust.
to ensure its results always align with the IEE 754-2019 standard.
So it's like the superhero version
Yeah.
of our addition algorithm.
Exactly.
How does it manage to be so robust?
Scaling.
Yeah.
If AA full detects a potential overflow, it scales the inputs down
Okay.
by dividing them by 2 before feeding them to fast2sum. This prevents overflow during the initial calculation
Okay.
and allows for more accurate adjustments later on.
Okay.
It even includes a check to ensure the sign of no 0 is correct when it's 0.
So AA full is like a seasoned tightrope walker,
I like that.
carefully adjusting to stay balanced.
Yes, always staying balanced.
Now, what about augmented multiplication?
So for that, we have algorithm 8, or AM simple.
AM simple.
It calls fast to mult to obtain no no,
Okay.
and then uses recomp to derive the final no de no and din.
Sounds familiar, but I bet it's not that straightforward.
You are correct.
Okay. What are the limitations this time?
So AM simple only works correctly for a specific range of input values.
Okay.
If the product is too large or too small,
Yeah.
it can run into problems.
Okay.
And just like AA simple, it might get the sign of 1 wrong when it's 0.
Those pesky sign issues.
They keep coming back.
And range restrictions, too.
Yes. AM simple is a bit more delicate
It is.
than its addition counterpart.
But I'm sure there's a more robust solution.
Of course there is.
Okay, tell me about it.
Algorithm 9, or AM-FUL, is designed to handle all possible input cases.
Full.
Yes, and prevent those overflow issues,
Okay.
ensuring that the results always align with the standard.
How does it do that?
It uses a clever combination of checks and scaling,
Checks and scaling,
adapting to different situations.
like a chameleon.
Exactly.
All right.
So AM-FUL first checks if the rounded product is infinity.
Okay.
If it is, it scales the inputs down to avoid overflow,
Okay.
and then uses fast-to-mult and a few additional checks to get the right result.
Gotcha.
If the rounded product isn't infinity, but is very small,
Yeah.
it scales the inputs up to ensure the product can be accurately represented,
So it scales up or down as needed.
just like a skilled climber.
What about those cases where the product isn't infinity,
Yes.
but still falls within that range where AM simple struggles?
AM-FUL has a strategy for those too.
Okay.
It scales the inputs up by a factor of 2p
Uh-huh.
and then makes careful adjustments.
Wow, AM full really is like the ultimate problem solver.
It is designed to be.
Adapts to any situation.
And always delivers the correct result.
Always.
That's the goal.
That's good to hear. So to prove that these algorithms work,
The authors used a formal verification tool called Coke, along with a library called Flock,
Okay.
to partially prove the correctness of these algorithms.
So they didn't cover every single edge case.
Not every single one. Those proofs provide a strong level of confidence.
That these algorithms are reliable.
Exactly.
That's good.
They also implemented these algorithms and compared their performance to an integer-based emulation approach.
And how did that go?
Well, the integer-based approach was much slower and more complex.
So a trade-off between speed and complexity.
Exactly.
Like race cars versus a slow-moving truck.
A great analogy.
So we've journeyed through floating point arithmetic,
We have.
explored rounding modes,
Yes.
and unpacked those clever algorithms for emulating augmented operations.
It's been quite a journey.
It has. And who knew floating point arithmetic could be so fascinating?
It's full of surprises.
What's exciting about these augmented operations?
Well, their unique rounding mode can really improve the reliability and reproducibility of numerical computations.
In lots of different fields.
In a wide range of fields, from scientific simulations to financial models to machine learning.
So it has a lot of potential.
Does a lot of potential.
What would you recommend for our listeners who are eager to learn more?
I highly encourage everyone to dive into the source material.
I've read it.
The paper explains these algorithms in detail, and the authors have made their implementations available.
Oh, wow. So they can really experiment with these concepts.
Exactly. You can see these algorithms in action.
That's pretty cool.
You can also explore how these augmented operations might influence new hardware in the future.
A challenge for our listeners.
It is.
Thank you for guiding us through this deep dive.
The pleasure was all mine. Until next time.